Okay, beta. So now if we arrange shells, shells means principal quantum number, and subshells, orbitals, and electrons, then the arrangement will be like this. If principal quantum number or shell number is 1, so first shell has only one subshell, that is the s subshell, which has only one orbital, and this orbital is s orbital, and maximum 2 electrons can be placed in this orbital. So you will place 2 electrons here, like this, one electron and the other electron. So these electrons are actually maximum electrons. So the 2 electrons of first shell are actually present in s orbital. Okay. If you talk about second shell, or principal quantum number 2, second shell has 2 subshells, that is s and p. S subshell has one orbital, that is known as s orbital, and p subshell has 3 orbitals, like this. And these 3 orbitals are named as px, py, and pz. These are the names of these 3 orbitals. Okay. Or precisely, you can say 2px, 2py, and 2pz, because these orbitals are from second shell. That is why we are writing 2 with px, py, and pz. Now, in total, 2 electrons can be placed here, and 6 electrons will be placed here. So in total, 2 plus 6, 8 electrons can be placed in second shell. So 8 electrons of the second shell are placed like this: 2 electrons in s subshell and 6 electrons in p subshell. Now, if you talk about principal quantum number 3, so third shell has 3 subshells, that is s, p, and d. S subshell has one orbital, which is s orbital. P subshell has 3 orbitals. Now, these 3 orbitals are named as 3px, this one is 3py, and this one is 3pz. And d subshell has 5 orbitals. So 1, 2, 3, 4, and 5. Okay, so the names of these d orbitals are not required in AS. Inshallah, you will come to know about the names of d orbitals in A2. So now in total, 2 electrons here, 6 electrons here, and 10 electrons in d subshell. So total it makes 2, 6, and 10. Total electrons that can be placed in third shell are 18. So maximum electrons in third shell will be placed as 18. If you talk about principal quantum number 4, so fourth shell has S, P, D, and F, 4 subshells. So S subshell has one orbital, P subshell has 3 orbitals, D subshell has 5 orbitals, and F subshell has 7 orbitals. This is 1, 2, 3, 4, 5, 6, and 7. So now in total, 2 plus 6 plus 10 plus 14, since each orbital can accommodate 2 electrons, so total electrons that can be placed in this fourth shell are 32. Okay. Now there is another rule that if you are to place electron in a subshell, then you will place electrons with the same spin first, and then the electron will be paired up if more electrons are available. So in a subshell, electrons will be placed with same spin first, then will be paired up. Now, how to explain this rule with examples? Let us say if you have 4 electrons in p subshell, suppose we have to place 4 electrons in p subshell, we have p4. So now there are 2 possibilities, that 4 electrons in p subshell, we know that p subshell has 3 orbitals. So we can place 4 electrons like this, 1, 2, and 3, 4. And the other arrangement will be like this: 1, 2, 3, and then 4. So now in the later arrangement, what we did, we placed electrons with the same spin first, and then we went for the pairing up. This arrangement is correct, while this arrangement is incorrect. Okay, because according to the rule, we are supposed to place electrons with the same spin first, then we are allowed to pair up. For example, if you have 5 electrons in d subshell, so we know that d subshell has 5 orbitals. So if you place these 5 electrons like this placement is against the rule, will be considered incorrect. So rule suggests that you have to place electron with the same spin first, 2, 3, 4, and 5. So if you place electron with the same spin, then this kind of arrangement appears, and this arrangement is considered to be correct. Okay. So while placing electrons in a subshell, we are required to place electron with the same spin first, and then we will proceed for the pairing up. Okay. Now, because the next concept is energy order. Energy order of orbitals. So we have to consider, or we need to know the energy order. Let us say, if I say that low energy orbitals are here on the left side, low energy orbitals, and high energy orbitals are here on the right hand side. High energy orbitals. So now how to arrange orbitals? The lowest energy orbital is this one, 1s. So 1s orbital has the lowest energy. Then comes 2s. Then comes 2p. Then comes 3s. Then comes 3p. And after 3p on energy axis, the energy order is for 4s. So on the axis, 4s comes after 3p, and then comes 3d. So this is the point you need to remember or memorize. You need to note this thing. In fact, you need to memorize this thing. That 4s orbital has lower energy than orbitals present in 3d. And then comes 4p, and then comes 5s. So you need to know till 5s in your syllabus. According to your syllabus, your discussion will be restricted till 5s. But this point is important. You need to know that 4s orbital has lower energy than 3d. Okay. So now there is another rule, and this rule is for placement of electrons. And the rule is that electrons will be placed in low energy orbital first. Low energy orbitals first. And then will be placed in high energy orbitals. Placed in high energy orbitals in ascending order. In ascending order. So you need to place electrons in the low energy orbital, and then electrons will be placed in high energy orbitals in ascending order. If you do this, this will be termed as electronic configuration. Electronic configuration. Now, better for electronic configuration, you need to write the orbitals like this. Sorry, this is electronic configuration. For electronic configuration, you need to write orbitals like this. Like first shell has only one subshell, that is s. Then comes second shell. Second shell has two orbitals, 2s and 2p. Then comes third shell. So third shell has 3s, 3p, and 3d. Then comes fourth shell. Fourth shell has 4s and 4p. And then comes fifth shell. So we are restricted to discuss till 5s in this syllabus. Now note this point. Carefully note this point. That for electronic configuration, we write 3d first and 4s then. 3d will be written before 4s in electronic configuration. But electrons will be placed in 4s first, then in 3d. Placement of electron will be done in 4s first, then in 3d. But in terms of writing, 3d will be written before 4s. So, for example, if we write electronic configuration, I think you should note this rule as well, that electrons will be placed in 4s first, then in 3d, because energy of 4s is lower than energy of 3d. Okay, so here we come with electronic configuration of transition metals. So how to proceed for transition metals? Suppose vanadium's proton number is 23. Since proton number is 23, it means electrons are 23 in vanadium. So how to place electrons? We are writing 1s, then 2s, then 2p, then 3s, 3p. 3d should be written before 4s. Okay, but electrons will be placed in this order, that the lowest energy orbital is 1s. We place 2 electrons here, then we place 2 electrons here, then we place 6 electrons here, then 2 electrons here, then 6 electrons here. So till this very point, 18 electrons have been placed. Okay, and now we are left with 5 electrons. 18 electrons have been placed till 3p6. So how to place the remaining 5 electrons? We need to place electrons in 4s first, because 4s has lower energy. 4s has lower energy than 3d. So that is why we are placing electrons in 4s first, and then we are left with 3 electrons, so we place electrons in 3d. Now the last electron is placed in d subshell. Last electron placed in d subshell. So that is why we say that vanadium is d block element, and this d will be small d, not the capital D. This d should be small d. So we say vanadium is d block element, because the very last electron is placed in d subshell. That is why vanadium is d block element. In fact, all transition elements are d block elements. So the last electron is placed in d subshell in all the transition elements. Okay, so now you can practice for various transition metals. Like if I take cobalt, proton number of cobalt is 27. It means that you have to place 27 electrons. So 2 electron in 1s, then 2s2, then 2p6, then 3s2, then 3p6. So till this point, 18 electrons have been placed. Now after 3p, we have 3d and 4s. So since 4s has lower energy than 3d, we are required to place electron in 4s first, which are 2 electrons. So 18 and 2 makes 20 electrons. And now 7 electrons are left. So we place 7 electrons here. Since the very last electron placed in D subshell, last electron placed in D subshell. So that is why we say that cobalt is D block element. Cobalt is D block element. In fact, all transition elements are D block elements. So we say that all transition elements. So all transition elements are D block elements. All transition elements, they are D block elements. Because in all transition elements, the last electron is associated or involved the D subshell. Okay. Now, there is another concept, and the concept is for unpaired electrons. As I checked the assignments, so I came to know that many students went wrong for unpaired electrons, number of unpaired electrons. So you need to be very sure about unpaired electrons. Now, if you have 1s2, it means that there is no unpaired electron. 1s2 means that both electrons or the orbital is paired. 2s2 orbital is paired. p6, all the 3 orbitals are paired. s2 paired. p6 paired. And 4s2, the orbital is paired. So if the orbital is full, or if the subshell has maximum number of electrons in it, then no unpaired electron will be present. But now if you notice this 3D can occupy 10 electrons. But right now this 3D has 7 electrons. So you need to make sure, it would be better that if you draw all the orbitals and place these 7 electrons according to the rule. And the rule was that you have to place electron with the same spin first. So these are 5 electrons, the 6 electron comes here, and the 7th electron comes here. So 1, 2, and 3 unpaired electrons will be present in cobalt. So for unpaired electron, one need to be very clear. If you have some kind of confusion, it's better that you draw the electrons in orbitals. It's better that you draw the subshell and then place electrons according to the rule, and then count the unpaired electrons. So this will precisely lead you to the correct number of unpaired electrons. Now, if you consider this one, all the subshells are completely filled. All the subshells are completely filled except this subshell. This 3D3 is not complete. Rest of the subshells are completely filled. So if you place 3 electrons in this D subshell, we come to know that there are 3 unpaired electrons. So in this way, we can monitor the number of unpaired electrons. Okay. Now, but the next rule you need to know is for chromium and copper. And the rule is that 1 electron jumps from 4s to 3d in chromium and copper. You have to apply this rule for chromium and copper. For example, I'm taking chromium, proton number 24. So 1s2, 2s2, 2p6, 3s2, 3p6. Till this very point, 18 electrons have been placed. So what comes after 3p, 3d, and 4s? But according to rules, we are to place electron in 4s first and then in 3d. 18 electrons have been placed till 3p. We are left with 6 electrons. So in 6 electrons, if you place 2 electrons here and 4 electrons here, this configuration will be considered incorrect. You will get no marks if you write chromium configuration like this, because the rule says that in chromium and copper, 1 electron jumps from 4s to 3d. So the correct configuration for chromium will be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d5 and 4s1. Now for unpaired electrons, once again, I'll refer to the assignment given to you people, and some of the students made mistake regarding chromium's unpaired electron. So D5, if you have confusion, it's better to draw the orbitals and then place D5. So just make D5 here and S1 here. So 5 electrons in D subshell will be placed like this with the same spin, and S1 will be like this. So this clearly shows 6 unpaired electrons. And the same rule is applicable for copper. Copper's proton number is 29. So if we go like this, 1s2, 2s2, 2p6, 3s2, 3p6, 3d, and 4s, till this very point, 18 electrons have been placed. And now we are left with 11 electrons. So if you place 2 electrons here and 9 here, this configuration will be incorrect. So what you have to do, that 1 electron should be transferred from 4s to 3d. So correct configuration for copper is 1s2, 2s2, 2p6, 3s2, 3p6, 3d, and this will be for S1 and 3D10. This is correct configuration of copper. Okay. Now the next thing is transition metal ions. Now configuration of transition metal ions is somewhat a tricky concept. Transition metal ions. Transition metal ions configuration should be done with care and with a lot of focus. Majority of the students did transition metal ions configuration incorrect in the assignment. The assignment I received and I checked, and I came to conclude that many of the students made incorrect electronic configuration for transition metal ions. So that is why just carefully listen that how to proceed for transition metal ions configuration. For example, if examiner asks us to write electronic configuration of manganese, proton number is 25. So it is my advice, once again I'm advising that whenever you are to draw electronic configuration of transition metal ion, better to draw transition metal atoms configuration first. Okay, it is advisable that to draw electronic configuration for transition metal atom first. So for manganese ions, better to draw configuration of manganese atom first. So 1s2, 2s2, 2p6, and then comes 3s, 3p, 3d, and 4s. So we have to place 25 electrons. So 2 here, 2 here, 6 here, 2 here, 6 here. Till this very point, 18 electrons have been placed. So then if you place 2 electrons here, it becomes 20 and 5 electrons here. So this is configuration of manganese atom. Okay. And now from this manganese atom, try to trace configuration for manganese tripositive ion. So now we, you know that positive ion is formed by the removal of electrons. So we have to remove 3 electrons. So you need to remove 4s electrons first. Remove 4s electrons first, and then remove electrons from 3D. So this is the rule for transition metal ions. For transition metal ions, you are required to construct transition metal atoms configuration in rougher, and then you have to remove electrons from 4s first, because 4s is the valence shell. Because electrons will be removed from valence shell first, then the electron will be removed from the inner shell. So you have to remove electron from 4s first, and then from 3d, because 4s is valence subshell. So you know electrons will be removed from valence subshell first, then from the inner shell. So if you remove 2 electrons from 4s and 1 electron from 3d, you will get this kind of arrangement: 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d4. So this is the correct configuration. Okay, this is the correct configuration. Now, what mistake majority of the students do in transition metal ions configuration? What students do? How they construct configuration of transition metal ion? This is a common mistake which you people also made in assignment which I gave you. Students take that 25 electrons were there in manganese, and 3 plus means that 3 electrons are removed. So if 3 electrons are removed, we are left with 22 electrons. Then they configure for 22 electrons like this: 1s2, 2s2, 2p6, 3s2, 3p6. And then what students do, which is wrong practice, after placing 18 electrons like this, they think that now 18 and these are 22 electrons, so 4 electrons are left. So they place 2 electrons here and 2 electrons here, because they consider that electron should be placed in 4s first and then in 3d, which is a rule for transition metal atom. You have to place electron in 4s first, then in 3d. This would be done in transition metal atom only, not to the transition metal ion. So they do this wrong practice. They apply the rule of transition metal atom to transition metal ion, and then they end up with wrong configuration. This configuration will be wrong. Now consider this is correct configuration. This one is correct. This one at the end is wrong. This one at the end is wrong. Now, this one at the end, what it is showing? That valence electrons are not removed and inner shell electrons are removed, which is absolutely wrong. It does not make any sense. Electrons should be removed from the valence shell first, then should be removed from the inner shell. So this is common mistake which students do for transition metal ions. So I would like to summarize this discussion. I will summarize it is, summary will be that for transition metal atoms, for transition metal atoms, you have to place electrons in 4s first, then in 3d. But this rule is not for transition metal ions. This rule is not for transition metal ions. What you need to do for transition metal ions, it is advisable So my advice is to draw configuration of transition metal first, and then remove electrons from 4s first, then from 3d. Okay, so for transition metal ions, it is better to draw the configuration of atom first, and then remove electron from 4s first, and then remove electron from 3d. Just take one more example. Let us say if I'm taking nickel example, proton number of nickel is 28, and I want to make configuration of nickel tri-positive. So I need to make configuration of nickel first. So it will be like this: 1s2, 2s2, 2p, 6, 3s2, 3p, 6, and then 3d and 4s. So since this is transition metal atom, this is not the ion. This is atom. This is not the ion. So for atom, you are to place electrons in 4s first, and then in 3d. So when I place electron in 4s, then I'm left with 8 electrons. So 8 electrons will be placed here in 3d. Okay. Now, for transition metal ion, the ion is tri-positive. It means that 3 electrons have been removed. So these 3 electrons will be removed like this: that you have to remove electrons from 4s first, and then you have to remove electron from 3d. So the configuration of this ion will be like this: 3s2, 3p6, and this is 3d7. This is nickel tri-positive. Now the mistake which students do, once again, this is a wrong practice which majority of the students follow. And what students do, they do like this: that 28 electrons are available, but tri-positive means that 3 electrons are removed from 28, so 25 electrons are left. So then they place 25 electrons like this: 1s2, 2s2, 2p6, 3s2, 3p6, and then from 3d and 4s, the wrong practice is to place 4s electrons and then 5 electrons here. So this thing that placing electrons in 4s first, then in 3d is not for the ion. It is not for transition metal ion. That is why this configuration is wrong. This configuration is wrong because this shows that valence electrons are not removed and electrons are removed from the inner shell. So how it is possible that electrons are removed from the inner shell without being removed from the valence shell? This is wrong configuration and this is correct configuration. So once again, I'm telling you that for transition metal atom, you have to place electron in 4s first, then in 3d. But for transition metal ions, you have to remove the 4s electron first, and then you have to remove electrons from 3d if required. If required. Yes, as far as unpaired electrons are concerned, so just you can consult here. This is D7. So D7 can be taken like this. This is 1, 2, 3, 5 orbitals. So 1, 2, 3, 4, 5, 6, and 7. This shows that 3 unpaired electrons. 3 unpaired electrons are present. The rest of the subshells are completely filled. So 1s2, 2s2, 2p6, 3s2, 3p6. They are all filled. So if the subshell is completely filled, it automatically shows that it has no unpaired electron. As far as nickel atom is concerned, all the subshells are completely filled except this D8. D8. This D subshell is not completely filled. Rest of the subshells are completely filled. So D8 means 1, 2, 3, 4, 5, 6, 7, and 8. This shows that 2 unpaired electrons are present. So remember one thing, that you need to be very careful for unpaired electron and you need to be very careful for transition metal atom and ion configuration. Okay. Now for the elements other than transition metal ions, you can proceed other elements. Other elements mean that non-transition elements. Non-transition elements. You can directly calculate electrons for ions as well as for atoms. Directly, you are allowed to place electrons. For example, sodium, proton number is 11. Sodium is non-transition element. So just straight away place electron. The electronic configuration for non-transition element is not that tricky. Only the transition metal atoms and transition metal ions configuration is a bit tricky. So for sodium, we place 1s2, 2s2, 2p6, and 3s1. These are the 11 electrons we place like this. So here the last electron is placed, the very last electron is placed in S subshell. So sodium is S block element. Sodium is S block element. Okay, and unpaired electrons will be checked like this, that all these subshells are completely filled. But this S1 suggests that there is one unpaired electron. Now, if you are to write configuration of sodium 1 plus, then no need to consider the parent atom here. For non-transition elements, you can directly calculate that proton number is 11, but remove 1 electron from 11, so you are left with 10 electrons. So in this way, directly you can proceed you can directly calculate number of electrons from the ion for non-transition elements, and then configure those electrons in terms of electronic configuration. Like you are to write electronic configuration of oxide ion, so no need to write configuration of oxygen atom. That advice was for transition elements only. I advise that write configuration of atom first. That advice was for transition elements. So for non-transition elements, directly conclude electrons. There are 10 electrons in oxide ion. So directly proceed like this: 1s2, 2s2, and 2p6. Okay. So this was kind of summary for the electronic configuration. And yes, when you are doing configuration, do notice that to which block the elements belong, and do notice the unpaired electrons. For example, if I write for boron, so proton number of boron is 5, so its configuration will be 1s2, 2s2, and 2p1. So the last electron is placed in p subshell, so this is p block element. This is p block element because the last electron is placed in p subshell. And if I write for potassium, so potassium proton number is 19, so this is 1s2, 2s2, 2p6, and then 3s2, 3p6. So till this point, 18 electrons have been placed. So what comes after 3p, 3d, and 4s? But between 3d and 4s, we have to place electron in 4s first. So only one electron can be placed in 4s. So this makes total 19 electrons. So since no electron left for 3d, so you can place either 0 here. You can either write 3d 0. Otherwise, you are required to remove 3d. So once you remove 3d, just place this 4s1 closer to 3p1. This is how you will proceed for potassium. Now potassium is S block element. Potassium is S block element because the last electron is there in S subshell. So this is some discussion for electronic configuration. Okay, one more thing which you need to know is that if you consider group number 1 and group number 2, in group number 1 we have lithium here with proton number 3, and then we have sodium, proton number 11, and then potassium with proton number 19, beryllium, proton number 4, and magnesium with proton number 12, and then calcium with proton number 20. So if we go for electronic configuration, for lithium it is 1s2 and then 2s1. So the last electron is placed in 2s1. So this 2 means that lithium belongs to period number 2. And S1 means that it is from group number 1. So if we draw configuration for beryllium, it will be 1s2 and 2s2. So this 2 means that beryllium is from period 2, and S2 is for group number 2. For sodium, since sodium is from period number 3, so the last electron will be placed in 3s1. So all group 1 elements will have S1 general configuration. Since potassium is from potassium is from period 4, sodium is from period 3. Sodium is from period 3, so that is why 3 is here, and S1 is from group 1. Potassium is from period 4, so it will be 4s1. 4 is for period, and S1 is for group number 1. For magnesium belongs to group 2, so it will be 3s2. Its last electron will be placed in 3s2. 3 is for period 3, and S2 is for group 2. For calcium, it will be 4s2. 4 is for period 4, and S2 is for group number 2. So that is why the last electron is being placed in both group 1 and group 2 in the S subshell. So group 1 and group 2 makes S block elements. And remember one thing, that all members of group 1 has S1 at the end. And S1 is like this. It means all member of group 1 has one unpaired electron. All members of group 1 has one unpaired electron. And for group 2, all members of group 2 have general configuration of S2. S2 will be like this. It means that all members of group 2 has 0 unpaired electrons. All members of group 2 has 0 unpaired electrons.